Hello, my name is David St-Pierre, and I will be presenting to you today about my final project for power engineering analysis entitled Creating Power Flow Records to Initialize Dynamical Simulations Using a Julia-Based Solver. Now, I will start the presentation by talking about my project objective, as well as the solution that currently exists. I will then discuss the solution that I developed as part of this project and the differences between these two. Next, I will discuss a little bit of an overview of the PowerModels Julia library, as this was a central point to my project. I will then discuss results of PowerFlow solutions and put an emphasis on the Milano 3-bus system. So first, to discuss the project objective, the first task was to perform a PowerFlow analysis on Milano 3-bus, the 7-bus system, IEEE 9, and the IEEE 14 bus. I also performed some PowerFlow simulations on the Nordic 44 bus, and those will be discussed in the presentation later on. The next part of my project was to create a GridCal 2Rec equivalent using PowerModels and Julia. I'll explain the differences about this in a couple slides. And lastly, to use the PowerFlow solutions that I create using my GridCal 2Rec equivalent in order to initialize OpenIPSL models in Dymola to perform dynamic PowerFlow solutions. The current existing solution is called GridCal 2Rec and was developed by Luigi's graduate student Sergio. And this program is based on the Python language using the GridCal library. And what this program does is it creates the PF data file structure over here in blue. What this file structure is a format that follows Modelica's record file. And what this has is the information from the PowerFlow solution in different files. So for example, in the bus data file, we'll see information such as the voltage magnitude and voltage angles for the various buses in the PowerFlow solution. Additionally, there's a loads file, a trafos file. The trafos file contains information about transformers, such as tap ratios, as well as machines data folder. When this program is used in conjunction with create pfrec, what this does, the create pfrec part, develops the file structure that's shown in the red box. When these two are combined, you have the entire Modelica record file structure that is required to initialize Dymola. Now, the solution I created for my project is different in the sense that instead of using Python and GridCal, I used the Julia language and the PowerModels library. Now, both of these two solutions use open source software. To explain the functionality in a little bit more detail, this figure over here shows that PowerModels 2Rec takes in a .m or .raw file. These files contain information about the bus structure, the different generators that are on it, and the transmission lines, etc. The .m file format is a special format specified by the MatPower specifications. So the program takes in these 4 files, parses them, and passes them to the PowerModels library. The PowerModels library then performs a PowerFlow calculation to find the solution. Similar to the GridCal 2Rec, the PowerModels 2Rec takes that PowerFlow solution and creates the PF data file structure containing bus data, loads data, all the other folders that are necessary for the record format. And again, when this functionality is used in conjunction with create PF records, we have that record structure that's needed by Modelica and Dymola to initialize the models for PowerFlow simulations that will be discussed in a little bit. But first, I want to talk about the PowerModels library itself, as this was such a central part of my project. To discuss what PowerModels library is a little bit, it's similar to other PowerFlow libraries such as GridCal, MatPower, or PSAT. It's as mentioned, it's a Julia library, open source, and it's equivalent to MatPower in the sense that it solves PowerFlow, but instead of using a piece of software such as MATLAB that costs money to buy, it uses the open source alternative Julia. And the developers of PowerModels were aiming to design a higher level feel to the language, but still maintain the lower level speed and performance that a lower level language such as C will use. Next, I wanted to discuss in more detail how the PowerModels to Rec program I created works. And to do that, I have a couple lines of code that I'd like to walk through. This first line here, power equals parse file. What this is doing is it takes the 7-bus, it takes this file, 7-bus case.raw, which defines the 7-bus grid structure. It takes that and parses it into this power variable. Now this power variable is a special variable that in Julia is called a dictionary. And I'll mention a little bit more about that in a second. This next line, again, takes the 7-bus input file, as well as the specification for what type of PowerFlow solution you want to solve, as well as a math utility that's passed to it. Now this is run through, this is where MatPower is actually being run with the run pf command. What this does is it takes that input file, runs the PowerFlow computation, and solves this, or saves the solution in this pf variable, which again is a Julia dictionary format. Now the way these dictionary formats work, as this was such a critical part of my project I wanted to discuss a little bit more, if you have the dictionary with the solution, to extract the solution you use a command like this. Then if you want to find, say, the bus voltage, the magnitude of the voltage on the first bus, you could use a command such as this line or the following 3 lines below it. Now once we have the parsed version of the bus system as well as the PowerFlow solution, we pass these 2 things to the PowerModels to Rec program. Now this is where the program that developed for the project is actually used. It takes these 2 dictionaries and a couple other parameters that are passed to it, and it creates this pf data file structure as shown on here. It additionally creates the pf results CSV file folder, and this contains files inside of it in CSV format that contain information about the PowerFlow solution. And these are useful to compare PowerFlow solutions, as I'll discuss in the next slide actually. Now to show an example of what's in one of these files, here's the PF bus file that was run for the 7-bus case. So we can see inside of here, this is the record format that Modelica specifies, and we can see the voltage magnitude on bus 1, for example, angle on bus 1, as well as for all the different buses in the system. Now, as I was saying, the CSV format is very useful because we can use that to compare the PowerFlow solutions with other PowerFlow solvers, and it just gives us good insight into what's happening. So on this slide, what I have is a comparison between the PowerModels solution that I achieved using the library compared to the GridCal solutions. Now in the lower right for the IEEE 14 bus, I didn't have data, so I don't have a comparison, but this is the PowerFlow solution presented here. However, we can see for the 7-bus case and the IEEE 9-bus case, the GridCal and PowerModels PowerFlow solutions closely match. Now for the Nordic 44 bus, which is shown in the lower left, there are some differences in around buses 15 and 20. To figure out which solution is valid, we would have to continue to run a dynamic PowerFlow solution. And that was the next part of my project, was to, now that I've done the PowerFlow, I need to verify that the solutions and the records that I've created are valid. And to do that, I import those solutions into Dymola along with an OpenIPSL model. So the figure down here shows an OpenIPSL model, the different buses, transformers, all the different transmission lines. And the record that I've created using PowerModels to rec is used as the initial conditions for all the different buses in this system. Now, if the solution that I have attained is correct, we'll notice that over time, the solution will be stable. If we plot the bus voltages, they will be flat over time. And this is because if the power flow is correct, the system is at equilibrium. It's at a valid solution. If it's not, as I show on to the right here, the initial condition, the starting condition is not flat. We see that over time, the bus voltages are changing as the system is trying to, if it can, reach an equilibrium point, which would then be the solution to the power flow problem. With the different models that I tested, I found that they all had a flat start, and this is good because it means the power flow solution, that PowerModels, and the records that I created were valid. So we can see again for the 7 bus IEEE 14 and IEEE 9 bus systems that the voltages on all those buses are flat over time, again meaning that this solution has been verified and we know that these are valid power flow solutions. Now the next system I wanted to talk about was the Milano 3 bus, because this gave me some difficulties. I was unable to achieve the same solution as the Milano book was able to. However, I was able to get a solution that I verified using 3 different power flow solvers. So to explain, I used GridCal, PowerModels, and MatPower to try to solve the power flow problem for the Milano 3 bus. And in the graph, we can see that for the first, second, and third bus, GridCal, PowerModels, and MatPower agreed. In bus 2, MatPower was slightly off, but very close to the solution. However, for the third bus case, the Milano solution did not match the MatPower, PowerModels, and GridCal model at all. And to make sure I wasn't making a mistake, I had my mentor Sergio, the graduate student, solve the Milano 3 bus using the GridCal library as well to achieve these same results. So it brings into question whether or not the solution in the Milano book is correct. However, the way to test this would be to import these power flow solutions into Dymola again as the initial solution, as the initial conditions, to see if over time the solution is stable. If we see the bus voltages are the same over time, we know that's the solution. If they're not, then we know that we don't have the correct solution. Now, in conclusion, my project was successful. I was able to achieve all the different goals. I successfully created a GridCal to rec Julia equivalent using the PowerModels library, and I was able to verify that PowerModels correctly solves the power flow solution and that my PowerModels to rec program works correctly by initializing OpenIPSL models in Dymola and achieving that flat start that shows that the solution is correct. And additionally, I was able to perform a power flow analysis on Milano 3 bus, 7 bus, IEEE 9, and IEEE 14 bus. So I thank you for your time.